So at this point, we're really taking a look at how many different ways we can come up with how to solve it. A lot of people end up focusing on, well, what's the right way? And we tend to either think of this is what we would normally do on it, and then that's all we do, or even just kind of freeze up with it being so open-ended like that. So let's kind of plant a few seeds here, seeing what we've done that's worked, some of the ideas that we've seen. What is one idea that you've come up with? Great. So we can set it equal to 0 and then factor. That would work. You may recall that's something that we did before, right? Where we had set the whole equation equal to 0 and then we would factor it. Okay, great. What else could we do? Yeah, great. We could still set it equal to 0 again, but then we could use the quadratic formula. Yeah, so in there's actually two different ways that this one could be done, where we could get our answer either just as a decimal, where we might round it, or we could leave it in exact form, where we like simplify the radical and just leave it with the radical in there. Yeah, we could graph it, right? Now, graphing definitely is a way, but there's actually different ways we could go about solving this by graphing. I think the way that you're referencing there, since we just said graphing, is we would graph the left and the right sides separately, and then we look to see where they cross. But of course, that's not the only way we could solve it by graphing. For instance, the first couple that we saw here, we set them equal to 0 first. You could even set this thing equal to 0, and then you could graph just that one side that you have left and look to see where it equals 0. So there's an idea where we set it equal to 0 and then substitute. We're wondering, is there a way that we can make that work? Because of course we've seen that substituting can be a useful tool, right? Do we know what we'd have to substitute in yet? No, because we don't know what x is. Could we still substitute something in to try to find our answer, though? We could try something, right? If we try a few different things, what do we normally call that kind of a method? Guess and check, yeah. So, yeah, we could do that, where we could substitute some stuff in, and then that's a guess and check method. Is that a valid method? Would that actually get us to a solution? Yeah. And hopefully they're whole number solutions or something like that, because if they're decimals, that's going to be a real pain to do. But it's a valid method. Let's see here. As we've been talking about this, nobody has suggested a method that I saw a lot of people working on. And so I want to take a quick little look at this over here, where I saw a lot of people where we tried setting, they got the x squared by itself, typically. And so that means we're adding the 9, so that gives me a plus 8 there. And then they tried taking the square root of both sides. Because if we do that square root, then the square root of x squared, of course, is x. So am I allowed to do the square root of both sides like that? Yes, that is okay. Has it proven helpful in this case? It doesn't look like it, because I don't have a way to simplify that part of the square root. Now, for a lot of times, though, that means that this is actually not solvable just by doing the basic algebra kind of stuff. And for the most part, that's true. In this class so far, we haven't actually seen a way where we could just move stuff side to side. We've always had to use quadratic formula or factoring or something like that. But as a slight little tangent here, there actually is a way you could solve it algebraically, where you would actually use this method that is called completing the square. Now, it involves basically taking it and turning the whole thing into one set of parentheses squared plus some number equal to some number. Because if we have it in that form, the vertex form, then we could solve it that way. Which actually is another way that I had just thought of, where we could find the vertex And then based on the vertex, we could write it in vertex form, and we could solve it algebraically from vertex form. And that's basically the idea of what completing the square is. Now, we haven't done completing the square in here. If you were really trying to solve this sort of problem and you didn't know how else to do it, how could you do it? How would you find that out? How would you find out that such a method exists? I always find it very interesting when we get to this point in this sort of a conversation. And at this point, I ask that question about what if we don't know how to solve a math problem? How could we solve it then? What would you do? Like if you were doing this problem on a homework and you had absolutely no clue, how could you still get an answer? Well, there's all sorts of tools out there. The internet is a tool. And there's lots of things on there, right? Now we could get into tons of nitty-gritty within that big umbrella. We could talk photomath, Mathway, all those different little equation solvers that are out there. Are there any other tools out there besides things that just do the work for you that would help you with this sort of thing? Yeah. Khan Academy or other various little like video lessons that would lead you through how to solve something.
Why would someone watch you how to do it rather than just...
Desmos is a very good tool for doing math. Yep. Yeah, and of course there's all those equation solvers. Yes, I still would put all those just under internet. Otherwise, I'd be here forever listening out all those. If you didn't have internet access and still needed to figure it out, what might you try doing? Yeah, you would talk to friends. Yeah, somebody said teacher. Turns out, yeah, you could always ask the teacher. That's why I'm here, is so that I can help you with such things. Or even you could even go to one of your old teachers. Like if you were out of school, you could always go back and be like, hey, I don't suppose you would be able to help me with this. Yes, that's okay too. And I might even put in a big umbrella here about experts in general being an option, because, I mean, it's not just teachers. You might know somebody who knows math really well, you know, a family friend, or your parents know somebody, or your parents know it well, all that kind of good stuff. If you know someone there who's an expert in being able to do it, then you could consult them as well. There's lots of options out there, right? And yet, when I asked you to come up with as many as you could, how many of us just had one or two, right? So many of us just got locked up on like just that first one or two options that we were thinking of, because they're the ones that we would typically use. But does that mean they're the only ones out there? And that's what I want you saying, because oftentimes a lot of what math is about, and it doesn't get communicated real well in math class, because we're always having to worry about teaching you a particular skill and then trying to get you some practice for that skill right away. A lot of what math as a subject area is actually all about, though, is actually a lot of creativity, where you have to figure out how can I manipulate these rules to be able to get us there. Now then, of course, there are some set things where there are those skills that I'm trying to teach you and get you used to, such as multiplying out polynomials. Remember, this is what we did yesterday, is we were seeing how we can multiply, for instance, a trinomial by a binomial. And we're going to continue practicing that skill today as well as some others. So go ahead and write this one down and multiply it out so that we can make sure you remember how that one works. So once we've multiplied them all out, everything in the first by everything in the second, we end up here. Now remember, we aren't totally done yet in this case, because we do need to look to see if we can simplify the final result here. And yes, we can actually simplify it. We got a couple sets of like terms here. We got the x squareds that we can combine, and we got the x's that we can combine. So we're going to go ahead and do that. And when you do so, you should end up here as your final answer. just x cubed plus 2x squared plus 3x plus 90. Now this was practice coming back to work that we did yesterday, but it's not all just going to be practicing what we did yesterday, but we are going to do a little bit more practice of stuff we did, boy, it's been a while now, probably about 3 weeks ago. I last asked a set of problems that looked like this. I'm going to see how well you remember. Factor each of these that you can. And notice I said factor if possible, because some of them will be factorable and some of them won't. All right, so let's check in, see how we're doing at least on those first couple. So this first one, let's go back and remind ourselves about how we talked about it before. We are factoring, which means that we're going to try to say what adds to this and multiplies to that. In this case, though, there's only one number here. Is that negative 25 what we're going to be adding to or multiplying to?
Multiply.
Yep, it's what we're multiplying to. And the reason why I know that is if you remember the normal ax squared plus bx plus c kind of formula. Remember, c is the number that we would normally be adding to. That's because it does not have the x on it. And so, yes, quite right, I misspoke. Multiplying to, thank you. C is what we're multiplying to because it does not have the x on it. And so the negative 25 does not have x on it, so that's how we know that it's what we're multiplying to. So if I'm multiplying to that, what am I adding to?
Nothing.
Yeah, there's nothing there to add to, right? Which means it is what number? 0, exactly. And so then we're left with a question about what two numbers add to 0 but multiply to negative 25. Is there such a pair? Yes. So I know I'm going to end up with my parentheses, each one starting with an x, and those two numbers were 5 and negative 5. Or negative 5 and 5. Again, remember, the order that you write those in does not matter, does not change anything. All right, and then we do the same thing with the next one, where we're looking to see what two numbers add to 0 but multiply to 49. Is there such a pair of numbers that adds to 0 but multiplies to 49? Let's see here. I heard a few different things all at once there. I heard 7 and 7. That multiplies to 49. Does that add to 0? No. Well, I can make them add to 0 if I make one of them negative, right? But now it multiplies to a negative 49. Okay, well, what if they're both negative? That multiplies to 49. What's that add to? Negative 14. Doesn't work. And for that reason, we can go ahead and conclude then that it is not factorable. As you may recall from when we talked about this the first time, we saw that it is factorable when it is x squared minus a perfect square. And it was not factorable when it was x squared plus, or if the number was not a perfect square. So, knowing that, go ahead and go through the other three if you haven't yet. All right, next up, x squared minus 1. Is that one factorable? Well, do we know what the square root of negative 1 is?
Yes, it is factorable.
Well, square root of 1, actually, I should say. Yes, it's 1. So yes, that means that one is factorable because we are subtracting a perfect square. The x squared minus 8, is that one factorable? Well, can we take the square root of 8? No, we get a decimal there. So for that reason, that one will not be factorable. The last one, is that one factorable? Well, 36 is a perfect square. Okay, so that's a possibility. Is it subtracting the perfect square? No. And so for that reason, that would not be factorable. So remember that in order for it to be factorable, we have to be subtracting, and the number that we subtract must be a perfect square. I have to be able to take the square root of it and get a whole number. So for instance, like in that first one, you'll notice when we subtracted that through, I got the minus and the plus, and the 25, the square root of 25, was 5. That's why both of those were 5s. And that pattern will be the same for every single one of those. And knowing this is actually going to prove to be super important with where we're going today. Because today, we're going to be doing problems like this, a little bit more factoring. But you notice these look a little bit different than the previous problems we've factored. And yet also not so different. There's a lot of similarities and a lot of differences going on here. And we're going to be looking to see today how the work we've already done in the past actually makes these not too tricky. We just got to learn a new rule. So, taking a look at that first one. Again, I was talking about similarities and differences, right? Let's start with those similarities. This one looks a lot like the quadratics that we were doing before, where before we dealt with a lot of quadratics where we would have, well, I'll even use the same numbers here. We might have been like x squared minus 23x minus 50. If I gave you something like that and said factor it, you know what to do. You know that you would say, okay, what two numbers add to negative 23 and multiply to negative 50? This is actually very similar to that, because you'll notice that it's like instead of that middle one being an x, it's an x cubed. And that first term that's an x squared, instead of being an x squared, it's x to the 6th, which is actually x cubed squared. I know, messing with your head now, right? But this equation that we're starting with, it's actually a quadratic in hiding. Because we're saying that instead of x, it's x cubed. But it still follows the same pattern as what our old ones used to, of it being x squared, and then the x, and then the number with no x's. Now, if this is bending your brain quite a lot, well, I'll try to make it a little bit more tame for you. We can actually formalize this into a rule that's going to allow us to do it. So if that's tough, we can get it down this way as well. Now, as you look at this rule, and you got it down in your notes, I hope that you can start to recognize in seeing this rule that this is actually the same rule as what we've been using. This is just a more generalized version of it. Because in the quadratics that we had before, we actually were working with the particular situation where n equaled 1. And if we do have n equals 1, then you'll notice then that the x is squared and the middle x is just an x, because we don't need to write x to the 1. And when you do that, then you end up with just plain old x's inside the parentheses as well. That was just a very specific case of this more general rule. And so then all that work that you already know about how to factor a quadratic can be used here. The only difference is that when we set up our two parentheses, I'm not just going to start each one with x. In the case of this first example, it won't be x, it'll be x what? Cubed. It will always be the same as this middle one, or half of the first one, whichever way you like to remember it. Because this only works as long as this first exponent is double the middle exponent. All right.
Makes sense.
And so now we're doing the same thing that we did before. We're saying what two numbers add to negative 23 and multiply to negative 50. And yes, it is negative 25 and a positive 2. So now, having seen that one done, take a look at the next one. Please go ahead and, on your own before we do it together, factor this one. All right, so for this next one, we are going to be able to factor it, so we're going to end up with the two sets of parentheses. But instead of starting each parenthesis with x, what will I instead start them with? X squared, exactly. So it's going to be x squared and x squared. And then I look and figure out, okay, what are the two numbers that add to negative 5 and multiply to 4? What are those two numbers? Negative 4 and negative 1. And so you'll notice that this is exactly the same kind of stuff as what you did when we were factoring quadratics, right? So it's the same idea. In fact, this is the easy type of quadratic to factor, right? So you're probably waiting for like the other one to come in, right? Where you're waiting for, okay, now what's going to be the part that makes it really hard and make it suck? There's not really anything that's going to be too bad in it, but there is one more layer potential in these, because you'll notice that this answer isn't actually completely factored. Because does x squared minus 4 factor further? Remember the problems that we just did before these? Yes. Does x squared minus 1 factor further? Yes. And so what you'll find is that some of these go a little bit further as a result. Now because of that, it might be well worth making an additional note to your notes here that once you break it down with these, that you want to check and see if those binomials factor any further past that. All right, so going back to this last one then, I can factor it further then, right? So what does x squared minus 4 factor into? What does it become? Well, it becomes 2 sets of parentheses, right? Each set of my parentheses, because I'm factoring the x squared minus 4, is each set of parentheses going to start with an x, or is it going to start with something else? Yep, it is just an x this time because I'm breaking up the x squared. And my two numbers, well, they're the numbers that split up the 4. And so then it becomes 2 and negative 2. And of course, the x squared minus 1, we already did that one, right? That was actually one of our examples that we did. So we know that that's going to be minus 1 and plus 1. All right, this is now considered fully factored because I was able to break down each of those parentheses as far as they could. Now, sometimes you're going to find a set of parentheses that doesn't break down any further. Like up here, x cubed plus 2, we can't factor that. And if that's the case, that one just stays that way. So you only break them down further if they do break down further. That's why with those 5 questions where I said factor them if possible, why I wanted you getting used to the idea of what makes it factorable and what isn't factorable, so that when it's not, you're going to know that, so that you don't have to keep trying to beat your head against a wall or trying to make something happen that's impossible. I'd now like us to try practicing that with a bigger problem. Please factor this one completely. So the very first thing is we set up our parentheses, and we see that since our original exponents are 8 and 4, that means that each of my parentheses will be starting with x to the 4th instead. And then I look to say, okay, what two numbers add to negative 17, multiply to 16, and you should be getting negative 1 and negative 16 there. Now, this has been factored correctly so far, but not yet completely, because we can still break them down further. So, will this first parenthesis break down any further? Yep, it will. It is an even exponent, and it is subtracting a perfect square. So that means, yes, that one's going to be able to go further. The second one, is that one going to factor any further? Yes, because it is also an even exponent, and it is subtracting a perfect square. And so then we know that our next line is going to be looking like this. And again, it's just a matter of finding the numbers. Now, of course, x to the 4th minus 1, we know what happens with that minus 1, right? We get 1 and 1. What are the numbers that we're going to get out of this 16? 4 and 4, exactly. And then we look at each of these and we say, are we done? Well, can any of them factor further? Yes. So we need to keep going. Does the x squared minus 1 here factor further? Yes, it does. Okay. Does the x squared plus 1 here factor any further? No. It's addition. And so that means that one will not factor further. The x squared minus 4, will that factor further? Yes, it will. So we're going to do that. And then the x squared plus 4 here, does that factor further? No, it is addition. And so you can see then that those two will break down more. So what do we do with the other two, this x squared plus 1 and the x squared plus 4? We leave them as they are. We're still going to have them in line with the rest of it, but they're not going to change their form. And so we know that we're going to be looking at something like this. And then it's just a matter of factoring down the x squared minus 1. That becomes minus 1 and 1, of course. And the x squared minus 4. which becomes minus 2 and 2. Do any of these parentheses factor any further? No. Because the ones that are subtracting a perfect square, they're just x's, not x squareds or x to the fourth or anything like that. And the ones that are an x squared, well, we already looked at those two and saw that we couldn't factor those two. So this then is completely factored at this point. This would be your final answer for the factorization. Well, when we did our quadratics work, we saw that not only could we factor them, but we could use that factored form in order to solve it. We can do the same thing with this type as well, where we can solve this degree 8 trinomial. And in fact, this particular one is going to be very easy because we've already done a lot of the work. Now, solving it actually isn't too tricky here, because step one of solving it is to factor it, if it's factorable. And of course, we know what the factored form of this already looks like, right? The only difference is that now my factored form actually has the equal 0 there before, because in the first problem, it was not equal to 0, so we could not say that it was equal to anything. But in this case, we can say it equals 0. All right, so now that we have this, remember that what we did with our factored form is we then used that to figure out what x equaled by figuring out what would make each of the parentheses equal 0. And we're going to set all of those parentheses equal to 0 and try to solve them, right? Although a lot of them are very fast. Like, what minus 1 equals 0?
1.
Yeah, 1. So there's one of our values, right? 1. What plus 1 equals 0? Negative 1. Okay, there's another answer. Now, I'm going to come back to this one here in a moment. What minus 2 equals 0? Okay, so there's an answer of 2. And what plus 2 equals 0? Negative 2. All right, now we're coming back and we're taking a look at these. Can I actually solve the equation x squared plus 1 equals 0? And the answer is going to be kind of. Because yes, I could subtract that 1 from both sides, and so I have x squared equals negative 1. Then I could take the square root of both sides, which would give me plus or minus the square root of negative 1. What is the square root of negative 1? You may recall that is I. And so the solution coming out of this particular term, the x squared plus 1, would be plus or minus I if we're supposed to include the imaginary solutions here. The question is, should we? Well, you may recall way back when we were first doing the imaginary numbers, we talked about how imaginary numbers are very much a niche kind of a thing. If you're expected to give the imaginary solutions, a problem really needs to identify to include the real and the imaginary solutions. And so because of that, and this one did not ask for the imaginary solutions, we don't have to give that as an answer. And so the same thing is going to happen with the x squared plus 4 over here. That would also give an imaginary solution, plus or minus 2i if you're playing at home. But we don't need to give that. We only need to give the real solutions. So I'm going to ignore those. So how do I know when to ignore them? How do I know when I should continue trying to solve it? If it doesn't factor, that's generally because it's not going to give you a real solution. And so all we're going to give here as our answers are the x equals 1, negative 1, 2, and negative 2. Those are the answers. If it said solve, include any real or imaginary solutions, then I would also include I, negative I, 2i, and negative 2i. But it didn't, so I don't. All right, so for this problem, it's asking us to find the zeros of the polynomial function. Now, this is not a term that I've used a lot in here. Normally, I will give you an equation set equal to the number, and I'll just say solve it. But this actually means the same thing. To find the zeros means to find out what makes the equation equal 0. So that's all it's saying, is what makes it all equal 0. So it's like saying set it equals 0, solve it. Well, What plus 1 equals 0? Negative 1. What minus 5 equals 0? 5. And what plus 6 equals 0?
6. It's negative 6.
That is it. That's all you got to do for these. All right, now looking at the second problem here, a lot of the answers here are very easy. You know, we got our 2, 4, negative 8, negative 3. But if there's going to be a question on this one out of anything, it's going to be about this, the x that is by itself. But it is another piece of this that is being multiplied by the whole thing. What can I plug in for x here? So what can I plug in for x at this point here that would make that whole little piece right there equal 0? 0. Yeah. Because if x equals 0, then it's 0 times the whole thing. So those are our solutions for that second one. All right, for the third problem here. I mean, a lot of it's pretty straightforward in terms of we should be able to look at and know, okay, I'm expecting 8 and I'm expecting negative 7. Great. But do I have to list the 8 twice?
No.
Do I have to list the negative 7 3 times? We do not need to actually repeat those, no. However, as a slight little tangent here, just so you know, the fact that the 8 comes up twice and the negative 7 comes up 3 times actually is significant. It's called the multiplicity of the solution. And that's actually going to be a concept that comes back more often when you get into pre-calc especially, because it affects how the graph behaves around that point and a few little things like that. So just kind of plant a seed there that that's the multiplicity of a particular solution. All right, so now we get into our last one there. Let's go ahead and take it piece by piece here. So the 3x squared, what can I plug in for x there that makes it equal 0? Yep, 0 is the solution from that. All right, next up, what plus 4 equals 0? Negative 4. Okay, great. Last part, 2x minus 5. 2 times what minus 5 equals 0? It's not 5. And sometimes that's the thing, is we get in this habit of only looking at the last number. And you'll notice in this case, of course, there's that 2 out front of x, which throws things off. Now, if you cannot just look at it and know the answer, write it out as its own little equation. I want 2x minus 5 to equal 0. So I could solve that. So I'd like add the 5 to both sides, and then I'd divide both sides by the 2. So x would equal 5 halves, or 2.5. And so those are our 3 solutions. All right, now these problems actually come up in 2 different guises. One way that you're going to see these types of problems come up is exactly this way, where I'm going to give you an equation, going to say what would the solutions be. The other way is that you should be able to also go backwards. I should be able to give you solutions, like I should be able to give you those, tell you what x equals, and say write an equation that has zeros at those 3 values, in which case you would then write this as your equation. Well, that's what I'd like you to practice doing now. Write the equation that would give these as the zeros. So on that first one, then I'm going to do y equals, well, it would have to be, in order to get the 3, I know it would have to be x and 3. I want to get an answer of negative 3. Does that mean I'm going to write x plus 3 or x minus 3? Plus 3. Yep. Because remember, I want to be able to say that negative 3 plus 3 equals 0. And so I do that for all 3 of them. So this is what your first answer would look like. All right, next one. If anything's going to throw you off in here, it might be the 0. When it's just going to be 0, what do we write? Yeah, that's just an x. Because technically you might be thinking, well, wouldn't it be x plus 0? Well, yeah, but x plus 0 is just x. So that means you might write something like this if we were just writing it all in order, but that looks weird, right? plopping that x in the middle like that, while it did follow the original order, it looks weird. So what I would suggest instead, take that x, put it out front. That way it's going to look the way that we're used to being able to see these. All right, then the next one. Fairly straightforward, except we do have the one little question here about, do I have to account for the fact that there's 3 negative 4s? When you're given 3 of them, yes, you need to account for that. But it's fairly easy. Because, of course, the negative 4 means we have x plus 4. 3 of them means cube it. So I just do x minus 4 cubed times x minus 3 times x minus 5. And so with that in mind, we then can go ahead and get our last one there. Now, as a little side note, these are the most basic answers that you could have given for these, but they're by no means the only ones you could have given. So, for instance, like this last one, if I'd made it 3x squared, it would still have all the same zeros, right? I could put any number I wanted to multiplied out front here, and it would still equal the same stuff. It would still have the same zeros. And so, why am I not putting those extra numbers in there? Just because why add complexity when I don't need to? However, I do want you to realize it still would work even if you did do that. All right. Next up, we're again shifting slightly. Notice we're doing all this different sort of solving polynomial stuff today. So we're continuing that theme of solving polynomials here. So what I'd like you to do is solve these 3. They all have a slightly different flavor to them. And so I'm partly doing this because we now need to be able to see what do I need to use when. So go ahead and write down each and solve them all, or at least take them all as far as you can, even if you get stumped. So for the first one, there's a couple different ways that people have done it. So like one way that I've seen is we add 121 to both sides, so we end up with x squared equals 121. Then we take the square root of both sides, and so you end up with x equals plus or minus the square root of 121. And the square root of 121 is 11, so that would equal plus or minus 11. That is one way you could have solved that first one. Another way is you could have factored it at the start. You wouldn't, instead of moving stuff side to side, you could have just factored it in this case. And then we could solve it and find that x equals negative 11 and 11 again. Same solution either way, you'll notice. All right, for this next one, x cubed equals 9x. There are a couple different ways you can do this one as well. I do want to take a look at both of them, though, in a little bit more detail. Because one way that I've seen some people do this one is start by dividing both sides by x. Okay? And so if we did that, if we divide both sides by x, then we end up with x squared equals 9, and then I can take the square root of both sides, and so I'd end up with x equals plus or minus 3. Okay, so note, if I do it this way, I get a solution of x equals 3 and negative 3. But there's another way I could do it. I could move everything to the same side and factor it. But when factoring this particular one, the very first thing I need to do is look to see if there's something I can take out of every single term. And you'll notice that there is an x in both of these terms. And so I'd start by factoring out an x. And then I could factor the x squared minus 9 after that. And so that, of course, gives me x plus 3 and x minus 3. And so what does x actually equal? X equals 0, negative 3 and 3.
Wait.
When I did it the first time, when I started by dividing both sides by x, I did not get 0 as an answer. But that's because this whole idea about dividing both sides of the equation by x, it is okay to do that unless x equals 0. Because remember, you cannot divide by 0. If you divide by 0, the universe implodes. Okay? So we cannot divide by 0. And so you'll notice that if you think back on all the algebra you've done over the years, when you've divided both sides, you'll notice that you've basically always divided by a number. and not divided by x. That's why. As soon as you start dividing both sides by x, weird things can happen. And so it is generally advisable to not divide both sides of an equation by x. Otherwise, you have to go and check and see if that's a solution that you just ruled out that should have been a solution at the start. Like some of you, I think, might have just looked at this original equation and said, if x is 0, that'll work, because 0 cubed equals 0, and 9 times 0 is 0. So you might have been able to see that right away. All right, let's take a look at the last one now. For this last one, just like I did up here, there was something I could factor out of both terms. Notice there's some factoring we can do here as well. So, what can I pull out of every single term? Well, I see 4 goes into everything. How many x's can I pull out of every term? 3 of them, yeah. So I can pull out 4x cubed. But if I pull out 4x cubed, I'm going to be left with a negative x squared. And then I'm going to have to work with that. So I'm going to tweak this just a little bit. I always like to be starting with a positive. And so I'm instead going to factor out negative 4x cubed. By doing that, my resulting quadratic is now actually very factorable. It was factorable even if I left the negative in there. It's just harder to do. So, what two numbers add to negative 5 and multiply to negative 24? Yeah, sounds like negative 8 and positive 3. So, there's our totally factored form. And once we have it in the totally factored form, then like we saw earlier today, all I got to do is figure out what makes each part equal 0.